Alright, this video is on VSEPR geometries and an attempt to show the difference between electron domain and molecular geometries. So if you want a cheat sheet with you or following along with this paper that goes through the 5 main geometries and then the molecular. So, okay, we'll see how this works because my setup here is a little funky. All right, so if we have a central atom that has 2 electron domains, okay, then that's going to give us a geometry of linear. And obviously the bond angle here is 180 degrees. All right, so that's your first main geometry is 2 electron domains, linear, bond angle of 180. The second geometry is 3 electron domains attached to your central atom, and that's going to give you a geometry of trigonal planar. Okay, it's flat, thus the word planar, and the bond angles here are 120 degrees. Okay, so this is 3 electron domains, trigonal planar. 4 electron domains is tetrahedral. Okay, and you can see very quickly that this is not planar at all, no matter how I rotate it. And so this is 4 electron domains, and the bond angles here, this is the funky one, the bond angles are approximately 109.5 degrees in a tetrahedral. 5 electron domains is an octet rule violator, and this is called trigonal bipyramid, okay, or trigonal bipyramidal. And this one has 2 bond angles, and this one's a little bit tricky for me to show you, but the first bond angle you can see is the bond angle here, which is 90 degrees, okay, and then of course another 90 degree, another 90 degree, okay, but the second bond angle appears when we tilt this on its side, and all of a sudden we have bond angles of 120 degrees, okay, so the trigonal bipyramid has 2 different bond angles, 90 and 120, 5 electron domains, and then 6 electron domains is another octet rule violator, and that would be this thing called an octahedral, okay? Now in this case, it doesn't matter how I rotate it, check it out, all the bond angles are 90 degrees, okay? It doesn't matter, this is a symmetric molecule. Now why octahedral when oct means 8? And this is confusing for students because this has 6 electron domains. And the reason that it's called an octahedral is because if we were to almost fill in the sides of this shape like triangles, okay, there would be 8 faces to this structure, and that's why it's called an octahedral. So those are your main geometries: linear, trigonal planar, tetrahedral, trigonal bipyramid, and then octahedral. So those are the ones that normally students don't have too much of a difficulty with, but it becomes then and when we start dealing with lone pairs on the central atom, that's where life gets a little bit trickier. Okay, no, we don't normally deal with a linear situation because linear is going to be linear, all right? It's going to have 2 electron domains, they're both going to be bonding domains, and this is just going to be the linear structure. Where it starts to go a little bit different is starting with 3 electron domains, which is the trigonal planar. Okay, however, what we're going to go through now is what happens if one of those is a lone pair. Okay, so if one of them's a lone pair, it's still there, it's taking up space, but it's not an atom and it doesn't count in the molecular geometry. And so notice this thing's geometry is what we call bent. All right, so 3 electron domains, but one's a lone pair gives me a bent molecular geometry. Okay, tetrahedral, 4 electron domains. Okay, what if one's a lone pair? This is called trigonal pyramid. Notice it's not planar, okay? It's trigonal pyramid. And then what if 2 of them were lone pairs? Bent. Okay, and these are the geometries that you're going to have to know from memory, and there's a lot of them. All right, trigonal bipyramid, 5 electron domains. What if one of them is a lone pair? This one's kind of the funny one. This is a seesaw, okay? Looks like a seesaw, right? So 5 electron domains, one's a lone pair, seesaw. 2 are lone pairs. It's called T-shaped because it looks like a T. Notice it's planar. Okay, and then 5 electron domains, 3 are lone pairs. linear. And last one, octahedral, 6 electron domains. If one's a lone pair, remember this is a purely symmetric molecule. If one's a lone pair, we refer to this as square pyramid. Why? Well, because the bottom of it is a square. Okay, and then if you kind of draw in your faces, it's a pyramid. So square pyramid. And if 2 are lone pairs, we take the opposite one. And this gives us square planar. Okay, remember the word planar means flat, and that's exactly what this is. So those are your 5 main geometries, and then, or what we call electron domain geometries, and then taking those electron domain geometries and breaking them into the molecular geometry.